Welcome to This Explainer. Okay, if you follow the tech world, you've definitely seen the headlines lately. People are out there predicting AI might achieve self-improvement in 6 months. And yeah, it sounds incredibly sci-fi, right? Like a model is about to enter some unlimited cycle of autonomous, unstoppable evolution. But we need to clarify this right off the bat, because understanding the actual engineering reality here is absolutely crucial if we want to separate real tech progress from pure science fiction. The reality? The near-term milestone is way more grounded. We're just talking about completing one full self-improvement cycle, not achieving unlimited recursive evolution.
It's the classic sci-fi hype versus reality. The hype promises this endless, unchecked growth, where the machine just keeps getting smarter forever. But the actual, realistic claim being made by engineers right now, it's firmly focused on completing a single closed self-improvement loop. That distinction is huge, and it completely changes how you should be viewing the next year of AI development.
So, here's our blueprint for today. First, the 6-month prediction. Second, the anatomy of one loop. Third, we'll look at a material science example. Fourth, the threat of recursive drift. And finally, the 3 milestones.
All right, let's dive into part 1, the 6-month prediction, and setting some realistic expectations.
Here's the deal. This whole near-term timeline, it's really just about proving feasibility. The claim is that the first complete post-training loop might become possible within roughly 6 to 12 months, basically establishing the core mechanism. Right now, highly paid engineers are essentially manually tweaking and debugging these systems. This milestone is about taking that manual, human-driven process of finding an AI's weakness and fixing it, and replacing it with a single automated cycle. It's essentially getting the AI to do its own chores for the very first time, just to prove it actually can be done.
Moving right along to part 2, anatomy of one loop, or the mechanics of self-improvement.
To pull off just one cycle, the model essentially has to look in the mirror. First, it has to identify a weakness in its own performance. Second, it needs to create new training environments tailored specifically to that failure. Third, it generates targeted training data to address the weakness. Fourth, it conducts post-training on itself using those new materials. And finally, the system has to self-verify whether the new version genuinely improved. If, and that's a big if, all 5 of these stages can operate together seamlessly, then boom, the system has successfully completed one closed loop.
Crucially, this first loop relies entirely on post-training. This is for sure the most plausible environment for this initial milestone. Why? Well, pre-training a massive model from scratch is insanely expensive, it eats up enormous computational resources, and the feedback cycle is painfully slow. Post-training, on the other hand, lets the system work with an existing model. The loop can operate rapidly, and the effect of the correction can be measured right away. This sheer speed and cost difference is literally why this specific mechanism matters so much right now.
Let's ground this with part 3, the material science example, putting the loop into practice.
Picture this. You've got an AI tasked with writing scientific code for material science. It attempts to write a script, but then it actually detects that its own simulations are unstable. That's the diagnosis. The AI then automatically creates specific tasks to isolate that weakness, generates its own training data, and retrains itself. Finally, it checks to see if its code writing capability actually got better. It's recognizing its own flawed simulations and teaching itself a better method without human scientists having to step in and hold its hand.
Completing just one loop in a domain like this would be a massive operational transformation. Today, a lot of AI development loops still depend heavily on human researchers to inspect failures, prep data, run experiments, and interpret the results. A system that connects all these stages automates a huge chunk of model development. It can generate way more experiments and respond to failures drastically faster than a human team ever could. Honestly, it represents a total paradigm shift from months of human research to minutes of machine compute.
But hold on, we need to talk about part 4, the threat of recursive drift, and why one loop just isn't enough.
We really have to remember that the R in RSI stands for recursive. Recursion means the output of one successful self-improvement cycle becomes the literal starting point for the next cycle, running again and again. For a genuine recursive system, the improved model has to diagnose its next weakness, generate new environments, train again, verify the result, and repeat that entire 5-step process over and over.
Which brings us to arguably the most critical hurdle in AI engineering right now. Can the improved system do it again safely and reliably? Because, think about it, the model changes after the very first cycle. Its behavior is fundamentally different. Its own internal evaluator might respond differently. The conditions for the next cycle change right along with it. It's kind of like trying to calibrate a telescope while the telescope itself is constantly changing shape. we have to ask if this moving system can stay stable while the very object being evaluated continues to shift.
The risks of repetition are pretty severe. You could have a wrong diagnosis in cycle 2. You could generate weak training data. You could have a false improvement, where the model just gets better at passing the test without actually improving its real underlying capability. Or you could have a hidden regression, where fixing one thing accidentally breaks another. If a weak evaluation method approves a false improvement, well, that mistake becomes the flawed foundation for the entire next round of training.
This compounding of errors is known as recursive drift. It happens when a tiny error in the first cycle accumulates over several cycles, eventually ballooning into something much larger than the original mistake. Solving this is incredibly tough because the system has to consistently distinguish genuine capability growth from temporary benchmark gains across multiple generations of change. And this matters immensely. An AI that gets really good at passing its own tests without actually getting smarter, that is a massive security and operational liability.
Finally, Part 5, the 3 milestones, charting the path forward.
The crucial takeaway here is that we are looking at fundamentally different engineering thresholds. Milestone 1 is completing one loop, where the system improves a specific capability exactly once. Milestone 2 is repeated loops, where each verified improvement acts as the foundation for a new cycle. And Milestone 3 is stable RSI, where many loops continue smoothly without that accumulated recursive drift we just talked about. Doing it once, doing it multiple times, and doing it endlessly without breaking down, those are entirely different evolutionary challenges.
When you map the timeline to these engineering milestones, things suddenly click into place. That 6 to 12 month prediction we keep hearing about in the headlines, that belongs strictly to Milestone 1. It is only about completing the first post-training loop. The timelines for repeated loops and fully autonomous, stable recursive self-improvement, those remain firmly in the unknown future.
So what is our central lesson for this explainer? A single closed loop is absolutely a massive breakthrough. It establishes feasibility, and it's going to trigger an operational transformation that changes how AI is built forever. But it is not recursive self-improvement. The first loop establishes feasibility. Only repeated, stable loops establish reliable, recursive self-improvement.
I'll leave you with this one decisive question to ponder. How many loops can remain valid before error, drift, or unstable evaluation begins to dominate the process? Ultimately, the real test of AI evolution isn't about how fast we finish the very first loop. It's about how many loops we can survive before the system breaks down.